How do you do, ladies and gentlemen, and boys and girls? I am Julius Sumner Miller once again, and physics is my business. And we come once more to the subject of heat and temperature. And this program we shall devote to this subject explicitly. How can we produce heat energy? How can we produce heat energy? Now, there are numerous ways which we can resort to produce heat energy. And first, supposing I have some water here, and this is something you must not ever do. Notice the firmness with which I make that sentence. Water. Supposing now I had here some acid of some sort, sulfuric, hydrochloric, some kind of acid added to water. Very dangerous business. The action, we say, is exothermic, releasing heat energy. You must never do it. But what am I suggesting? Chemical action is one way to produce heat energy. Chemical action. Another. Indeed, I'll approach it another way. There are various kinds of energy. Mechanical energy, acoustic energy, electric energy, magnetic energy, electrostatic energy, nuclear energy, electromagnetic energy. All of these kinds of energies can produce heat energy. And so we say that thermal energy, or heat energy, is a degenerate form because all the other forms can go that way to that one. Illustration. Here is a cup of tea which is cold. I want to make that cup of tea proper and adequate to drink. I propose to heat it. How could I heat it? I could heat it by stirring it in this way. Stirring it. Take me a long time, but I am converting mechanical energy to thermal. Or consider the following. Here is a beautiful one. Acoustic energy. And I have made this calculation. You know that it takes work for me to talk. Indeed, I ate food which has been metabolized, which makes available energy so that I can talk. So, the compressional waves that are emerging here involve an output of energy. I say that if I talked long enough onto that cup of tea, I would heat it up. Indeed, I've made the calculation. Ordinary talk produces about 100 ergs per second. And an erg is about 1/10,000,000th of a watt. So if I wanted to light this electric lamp or heat that cup of tea, you see it would take several 100,000,000 people talking for a long time, but it could be done. I'm suggesting the conversion of acoustic energy to thermal. Or consider another. Here is a slab of lead in which I have inserted a thermocouple. Now, you know what a thermocouple is? 2 wires of different stuff. I could connect this block of lead. There's the block of lead with 2 wires in it. I could connect this to a galvanometer, and I could hit that slab of lead in this fashion, and we would see an amazing thing. This galvanometer would show an electric current, which means that the junction here has suffered some rise in temperature. Or a better one. Here is a nail. I have done mechanical work on the nail. Now I'm going to pull it out. Oh, there it is. I have plenty of evidence that that nail is hot. Mechanical work. Or a better one. I like to do this one because it has much history of an enchanting sort. An electric drill. Hot. The wood chips are warm. And I am therefore reminded that mechanical work arising from electrical energy converts to heat. And I like to do this experiment because it brings to our attention this man, Count Rumford, William Thompson, a Yankee who turned British, who became German, who married Lavoisier's widow, who for the Bavarian government was engaged in drilling cannon and discovered that the chips got hot, and he threw the first light upon that very difficult subject of heat, which was originally called caloric. See, we get the word calorie. Or consider the following. In this tube, I have some lead shot, little BBs. Good. Supposing I weighed the lead shot, and I took the measure of this length. Clearly, I do certain mechanical work in raising the shot to the top, and then gravitational forces pull it down. The mechanical work I do is converted to heat. I could do this 10,000 times, taking the original temperature, finding the final temperature, getting the difference in temperature, and it is an elementary classroom exercise. If you know the mass of the stuff, the change in temperature of the stuff, the amount of mechanical work that was done on it, W-O-R-K, you could find, and, we would find what? The mechanical equivalent of heat. How much mechanical work does it require to produce heat? Answer. Look at here. This is fantastic. 778 foot-pounds of work to produce one British thermal unit. What does that mean? It means that I have to do 778 foot-pounds of mechanical work to produce enough heat energy to raise 1 pound of water 1 degree Fahrenheit. So I suggest, indeed, it occurs to me every time I take a bath, that enormous mechanical work has been required to heat that much water to that high a temperature for me to bathe. And it always brings me to think of that beloved Count Rumford, who married, as I say, Lavoisier's widow. Another. Here is an array of magnets, and inside a coil of wire. And here is a lamp connected to that coil. I'm going to do mechanical work on the coil. It requires a force to turn the crank, to turn the coil, and watch the lamp. Obviously, I have converted mechanical work to electrical energy, and the electrical energy has been converted to thermal energy because the filament in the lamp got hot enough for us to see. It emitted light. Or another wonderful one. Here is a slab of lucite, plastic. And here is a cat's fur. And I am going to do some mechanical work. Here is a metal plate with a handle. I'm going to put the metal plate down on top. I am not discussing the electrostatic changes that are taking place. I'm going to ground the upper surface of the plate. Oh, I felt something. And now, listen. Oh, there was a spark. I'm going to do it again. There's a spark. Indeed, here is a fluorescent lamp, and I think that if we quieted the lights in the studio, you will see that I have produced enough electrical energy. We need all the lights, I think, in the studio to see the lamp. Yes, I saw the lamp flash, but of course the lamp is too much lighted by the lights in the studio. Let me take another lamp. Here is a tube that is filled with neon gas, and I want you to see the flash of that tube. Watch it. Yes, I saw it. There it is. I'm going to do it again. And what have I suggested by this adventure? I have suggested that we can do some mechanical work on that dielectric, which is the slab of lucite, give rise to a separation of the charges, and then draw electrical energy from this system. And here is a comment about which I shall speak more adequately when I do a program on electrostatics. I can continue to draw this energy from this system forever without any diminution in its availability. That's a fantastic thing. Now somebody says, did you say, Professor, that you can continue to draw energy from this system forever without any diminution, any lessening in the amount of it? And my answer is yes. And forever is a very long time. Consider now another little classic, quite enchanting. There arises often this little problem. Here is a perfume bottle, and the glass stopper is lodged in it so firmly that it cannot be removed. Now, what do I propose to do? I propose to get out the stopper. There are all kinds of methods for doing this. Heating it in hot water, heating it with a flame, pouring some solvent down through where it fits. But here is a wonderful way to do it. A piece of string wrapped around the neck, and such action. Now, what am I emphasizing in all of this? I am emphasizing a very important subject, which is a terror for the human race. Friction. Friction. And what must we say about friction? We must say this. We spend untold measures of money and effort to minimize friction, reduce it, get rid of it. But is not this something to think about? If we were successful in eliminating friction, there could be no motion of any sort. Meaning that if friction were at this instant annihilated, undone, disposed of, I could not move from this place, except perhaps upward. Oh yeah, I could do that, but I couldn't go forward. Supposing I did go forward, I could never stop. So if now, at the switch of my fingers, friction were eliminated from the earth, all motion would be quieted. Every automobile would be brought to rest. All the ships on the sea would stop moving. Maybe the astronauts would keep going because they are in empty space, and having once acquired the motion, they go without effort endlessly. Now, where are we? Oh, more on the matter. Production of heat. Bicycle pump. You know, you connect it to your bicycle tire or your automobile tire, and you pump, and what happens? The piston gets hot. Heat energy converted from mechanical. Or consider a simple one that is most dramatic. Here is a paperclip. What shall we do? It is now at room temperature. I bend it. I bend it. I bend it. Uh-oh. I cannot hold it anymore. It is too hot. And what I would ask you to think about is the astonishing behavior internally of those little molecules and atoms of stuff which are put into fantastic agitation. And this is a mode of motion which describes this thing called heat. And I thank you for listening.